This question is from GATE 2014 Mechanical Engineering Paper Set 3, question number 40. A mass spring dashpot system with mass M as 10 kgs, spring constant K as 6250 Newton per meter is excited by a harmonic excitation of 10 cos 25t Newton. At the steady state, the vibration amplitude of the mass is 40 millimeters. Damping coefficient C in Newton second per meter of the dashpot is dash. Let's write the given information first. Mass is given as 10 kg. Spring constant K is 6250 Newton per meter. The external force or exciting force F is given as 10 cos 25t in newtons. So this is a function of time t, and the response X is given as 40 millimeters. The steady state response X is 40 millimeters. We need to find out C. So from the given data, we can see that using mass and stiffness constant, we can find out natural frequency of the system, omega n first. So omega n will be root over K by M, which will be equal to root over 6250 divided by 10. This gives us omega n to be 25 radian per second. Also, we can find out the critical damping coefficient Cc as 2 root over Km. This is a standard formula that has to be remembered for the exam, which will be equal to 2 into under root of 6250 into 10. So Cc comes out to be 500 Newton second per meter. Another hidden given data that we have is of omega, that is exciting frequency of the external load F, exciting load F. So omega is given to be 25 rad per second. Therefore, we have omega by omega n as 1. That means the exciting frequency omega matches with the natural frequency omega n. This is a condition for resonance. Now, we also have the steady state response X, which by formula can be given as X is equal to F naught by K, that is amplitude of the exciting force by spring constant K, divided by F naught by K gives us the static deflection, divided by root over 1 minus omega by omega n square whole square plus 2 zeta omega by omega n whole square. Now, the things that we already have is steady state response X, F naught is 10 Newton, K is given, omega by omega n we already found out to be 1. So by substituting these values and taking damping ratio zeta C by Cc, that is damping ratio is C, damping constant of the system by critical damping constant, which will be C by 500. Cc we already found out as 500. Let's substitute all these values and find the value of C finally. Therefore, we have 40 mm, that is 40 into 10 to the power minus 3 meter is equal to 10 Newton divided by 6250 upon. This term goes to 0 because this becomes 1 minus 1 whole square, that is 0 square. Root over 2 into C by 500. So this is 2C by 500 whole square. The square root and square cancels out each other. After rearranging, we can find out C as 10 into 250 divided by 40 into 10 to the power minus 3 into 6250. Calculating this in the digital calculator, we get value of damping coefficient C as 10 Newton second per meter. Let's go back and fill the answer. So the damping coefficient C of the dashpot is 10 Newton second per meter. To learn more about damped vibrations, you can refer to the NPTEL video W03M02 Forced Damped Vibration from the course of Structural Dynamics. The course is by Professor Raman Challa Pradeep Kumar. He is from Earthquake Engineering Research Center, IIT Hyderabad. I hope the solution will help you clear your doubt. Thank you.